inverse Fourier transform. So the proposition I had written here implies that E,
Could you tell us why do you need that function phi in there?
we need that phi in there.
Yeah,
because
why?
we need a continuous function.
So you want to smooth this out
Yeah.
so that Q is regular? Okay, that's zero.
So we eventually want to take the transform of P times this E. And we'll eventually get some convolution and stuff. We'll see. So E is smooth on Rn, not zero, and rapidly decreasing. As x goes to 2. So then we're going to take,
When you say rapidly, what do you mean?
it's based on the temper distribution, so faster than any polynomials.
Okay.
So then we're going to set V equal to P of V times this E. So from this, we're going to transform this Fourier transform. And we shall get V hat C is P of C E hat, which E hat is the inverse of this times this, or the transform of those. So we get P of C times 2 pi,
Well, you get 1 minus phi, right?
yeah. So I'll just put Q there. So E has the tilde, and we have the transform of that, so these two essentially cancel out. And we're left with just Q. And then we're left with C is constant, given by 2, and then we have the 1 minus P. 1 minus.
Well, P of C cancels the other one.
Oh yeah, I forgot about that too. So that cancels with that. We're just left with this. So we're going to call, then we take the and we're going to take the transform back, the inverse transform. And we'll get P of D E equals, so take an inverse transform of the constant. So isn't the inverse transform just 2 pi negative over 2?
Why did you put negative there?
Oh, okay. So then to transport this would be the delta function. Yeah, so we get the delta function from this. So get delta minus this constant. 2 pi over 2. Psi, the inverse transform. So we're going to call this thing W. And this W is an element of the Schwartz space. So this essentially equals delta plus W. So we use this W to prove the elliptic regularity, essentially.
What is elliptic regularity?
Oh, I need to define something else. So we have the W. We have the definition. Seems of F. So singular support.
By the way, why did you use that proposition I was asking a question, you didn't use it? That, you remember that
Yeah.
PM is an S1M and stuff like that? Did you need it at any point?
Well, I don't really know, but it just, because I didn't totally understand, so I thought I would need it maybe.
No, you didn't, okay.
So singular support is, some of this.
By the way, there is one place where you implicitly assume that the operator has constant coefficient. So look, you define that V equal to P of D on E, right?
Yeah.
And then you said the Fourier transform is equal to P of CE. That's only true if P of D has constant coefficient. If it doesn't have constant coefficient, then that's just not true.
Yeah.
And for operators with constant coefficients, I mean, all of this is almost trivial. I mean, you just do Fourier and you're done. Okay, go ahead.
So singular support, okay, so then the smallest set. So singular support of F equals K, so
What is K?
the K is the smallest set. K is the smallest set for which U is smooth on Rn not K. The smallest set for which U is smooth.
You mean F is smooth?
Yeah. F is smooth on Rn not K.
And for which is smooth?
So pretty much F is smooth everywhere except for K.
Well, what if you have two such points? Let's say you have singularity at 0 and singularity at some other point which are of the same size. Then what is a singular support?
It would be the set of those 2 points, I think.
What they say it's the smallest set for which this is smooth. Okay. So if it's one point, it just okay. You're basically removing the singularity. Okay.
Yeah. So for example, scenes of absolute value of x that's equals 0. So it's a set where pretty much you have singularities.
It's the set where it is not smooth. Okay, basically. But when you say smallest set, it's kind of.
So elliptic regularity this is defined as where U as a distribution on Rn. And we have our equation P U equals F. So P of D is elliptic. Then singular support of U equals singular support of F. So everywhere F is smooth, U is also smooth on. So that's elliptic regularity. So to prove that, we're going to use Yeah. For U be an element of this epsilon space, which is a set of compactly supported distributions, so it's 0 outside of the compact subset. We're still assuming the same thing, du equals f. So now we take convolution of E with f. So this also equals, so we take convolution of each side of these. So this equals to E convolution with P d U. And there's one step I don't really understand. They change this to P d E convoluted with U. So I'm not really sure how they did this.
Well, just write it as an integral and then integrate by parts and you'll see that. Just put an index y at d, so dx and y, just index y, yeah, here, yeah, just like y, not x. With x and y, okay? So now in this integral, integrate by parts, it goes to e. The whole operator p will act on e. If it changes, it will be the adjoint operator of that. If you just multiply all the operators by -1 to the alpha. You understand? It just will be p of minus d, basically.
So it's integration by parts.
By integration by parts, it is acting on e with p of negative d. You got the change sign of d when you do that.
But there's no negative here.
Well, that's because you change it. E should depend on x minus y, not on y minus x. Just write x minus y. X minus y. Okay. And now see, p of minus d with x on y is the same as p of dx acting on that because it is x minus y. Is that clear?
Yeah.
So and then you will get that formula.
Yes, we have this, and we have, we derived this before, which is that delta plus omega. Or W, I mean. Over U. And then this just equals U plus omega U. When we see that, just integral of U plus W. So you're going to solve the y, so this becomes U of x plus W convoluted with U, essentially. Does that make sense?
Yeah, I mean, that's good. Yeah. And then what?
So we have U, and this thing right here is an element of continuous functions. Yeah, same thing. We're almost there. Almost there. So now look at singular supports again. That element of the compact supported distributions. Seeing support of E convoluted with F is subset of C sub F. If
Why is this?
the book just said it's an exercise. I didn't really go.
So you computed E convolution F and you get U and then plus something smooth, right?
Yeah,
So basically it's U, the singular support of E star F is E U.
yeah,
But then you say this, that it is a subset of singular support of F, right?
yeah. That's the little other part I didn't get, because I, where did it go?
Well, if you knew that, then I guess that's the key point. I mean, this is pretty obvious.
So yeah, sinus soup.
If singular support of E is a subset of 0.
So we're supposed to like E composed of F.
Well, what do you mean subset of 0?
That's what the book wrote. Like, I
0
wanna
is just one point is equal to that, right?
So it's either that point or empty.
Yeah.
What?
Either that point or empty.
Oh, okay.
Because E has, supposedly has a singularity at 0, which the second half of the section is dedicated to, but I don't really want to go into that. So we have singular support of E, F, which is singular support of that. So it's